Hey guys, today's lesson is 7.5 part 3, trig form of a complex number. In the last two sections, we looked at writing complex numbers in trig form. We looked at multiplying, dividing, and raising those numbers to a power. In this section, we're going to look at taking roots of complex numbers in trig form. Let's start with an algebraic example. We want to find the sixth roots of the number 1. One way to think about this is what numbers raised to the sixth power equal 1, or x to the sixth equal 1. So this is an equation we want to solve. It's easy to think about the two solutions, positive 1 and negative 1. But remember, the fundamental theorem of algebra says if we're taking sixth roots, we should get 6 answers. We should get 6 complex roots. So one way to solve is setting it equal to 0. We can factor this expression using the difference of two squares. We can factor this using the sum of two cubes formula, and we can factor this using the difference of two cubes formula. Here are our solutions, negative 1 and positive 1, and to solve this trinomial, we would have to use the quadratic formula. Same with this. So we get two more solutions using the quadratic formula here, and two more solutions using the quadratic formula here, and you can see that we end up with a total of 6 roots. Unfortunately, the algebraic technique that we just used isn't going to work for every single problem, so we need another method. And we have a formula to find nth roots of numbers in complex form, in trig form. So let's say we have a complex number in trig form. Remember that z equals r cis theta. I'm using the simplified notation. It has exactly n distinct nth roots given by this formula. So whatever root you're trying to take becomes the root here, the nth root of the radius, cis, the angle plus 2 pi k all over n. Again, n is the sixth root or the third root or whatever root you are taking. And k is a new variable. K is a counting mechanism, and we start with k equals 0, and we go all the way up to 1 less than n. This ends up giving us the number of roots that we need, depending on what root we're taking. We're going to think about the same example that we looked at just a minute ago. We want to find the sixth roots of the number 1 using this formula. Well, first we've got to take the number 1, z equals 1, we're thinking of it as a complex number in standard form, and we want to write it in trig form. It has to be in trig form in order to use the formula. Well, this is an easy one. We can think about graphing. Remember, we have the real and the imaginary axes. The number 1 can be plotted right here. So we can see that the radius is 1, and the angle is 0 degrees or 0 radians. I'm going to expand this cis form and write it as cosine 0 degrees plus I sine 0 degrees. And now we're ready to apply our formula. So our goal here again is to find the sixth roots of the number, the sixth roots of the number. Using the formula, that would be the sixth root of 1 times cosine of the angle, in this case our angle is 0, plus 2 pi k all over n, and in this case n is 6. And we just repeat that expression over here with the I sine of the angle part. Now we're going to think about k. And k, we're going to start with k equals 0. So if k starts as 0, we can imagine plugging in 0 here. This whole expression becomes 0. And so we have the cosine of 0 plus I sine of 0. Well, cosine of 0 is 1 and sine of 0 is 0. The sixth root of 1 is 1, so we can think about 1 multiplied by all of that. And so we get the answer 1. And we're just going to go through over and over until we get the number of roots that we need. Next, we're going to use k equals 1. We can imagine plugging k equals 1 here. Well, that would just be 2 pi over 6, which simplifies to pi over 3. So our angle here would be 1 times the cosine of pi over 3 plus I sine of pi over 3. Well, cosine of pi over 3 is a half. Sine of pi over 3 is root 3 over 2. And then we can simplify this expression here. Next, we can think of k being equal to 2. So coming back up here, if k is 2, 2 times 2 is 4, this would be 4 pi over 6. 4 pi over 6 reduces to 2 pi over 3. We have the same exact angle here, right? So then we have the cosine of 2 pi over 3 plus I sine of 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. Sine of 2 pi over 3 is positive root 3 over 2, and we get this expression. So you're just going to have to continue each iteration, k equals 3, k equals 4, and k equals 5, and we stop here. We know to stop when k equals 5 because our goal was to find 6 roots. Since we started with k equals 0, once we reach 5, we have now found all 6 roots. And this is kind of a cool example because we can compare these 6 answers were the same 6 roots that we found when we solved algebraically. Here's a second example. We want to find the 5th roots of z equals 16 cosine 4 pi over 3 plus I sine 4 pi over 3. This is already in trig form, so we're ready to jump right into our formula. In this case, since we want to find the 5th roots, we're going to be using n equals 5. So we can also think of this as cis 4 pi over 3. And our goal here is to take the 5th root of this number, the 5th root of 16 cis 4 pi over 3. I'm going to think about writing out each term individually, starting with k equals 0. We're going to take the 5th root of 16 cis 4 pi over 3 plus 2 pi times 0 over 5 because k is 0 in this case. And we can simplify, this becomes 0, 4 pi over 3 divided by 5 becomes 4 pi over 15. In this example, 4 pi over 15 isn't one of those nice numbers that falls on the unit circle where we can easily evaluate the cosine and the sine of 4 pi over 15. So in a problem like this, I want you to just go ahead and leave it in trigonometric form. You don't have to worry about converting it back to standard form. If k equals 1, instead of 0 here we have 1. So you've got to do a little bit of work to simplify the fractions here, and you should end up getting 2 pi over 3. Again, since some of the roots end up being in trig form, you can just leave them all in trig form. We could simplify this, but we can just leave it in trig form. If k equals 2, we plug 2 here. 2 times 2 is 4. So we've got 4 pi over 15 plus 4 pi over 5. We've got to simplify fractions, add them together, and you should get 16 pi over 5. So we've got the 5th root of 16 cis 16 pi over 5. Or sorry, 16 pi over 15. And then you can see the other iterations, k equals 3 and k equals 4. There's a lot of work that goes into each one of these problems to find all of the roots. Since our goal was to find the 5th roots, we're going to stop when k equals 4. Let's take a look at one more example. Our goal here is to solve the equation x cubed plus 8i equals 0. X cubed plus 8i equals 0. Isolating x, we can start by subtracting the 8i term over to the other side, and then we want to take the cube root of x, the cube root of negative 8i. So our solutions are going to be the cube roots of negative 8i. So now let's think about this. Our goal is to take the 3rd roots of a complex number. That complex number is negative 8i. In order to use our formula, we've got to put it in trig form. Well, negative 8i, remember this is our imaginary axis, so negative 8i, I'm going to think about plotting down here. We can see that our radius is 8. Radius will always be positive. And the angle is 3 pi halves. So here's our complex number in trig form. Remember, our goal is to take the third roots of this number. Our goal is to take the third roots of this number. So we're going to do the third root of 8 multiplied by the cosine of the angle 3 pi over 2 plus 2 pi k all over n, the nth root, we're taking a third root in this case, plus I sine of the same angle, 3 pi over 2 plus 2 pi k all over 3. And now we've got to go through each iteration of k. Let's start with k equals 0. Well, we know that the third root of 8 is 2, so we've got 2 times this whole expression. If we put 0 in for k, we just end up with 3 pi over 2 over 3. So cosine 3 pi over 2 divided by 3 would be the same as times 1/3 plus I sine of that same angle. We can simplify a little bit. The 3's are going to cancel, and we just get pi over 2. So let's rewrite this. Cosine pi over 2 plus I sine of pi over 2. And thinking about the unit circle, the cosine or the x value at pi over 2 is 0. And the value of sine or the y value is 1. So we've got 2 times I or 2I as our first solution. Then we've got to use k equals 1. Thinking about plugging in 1 for k, we've got 2 times. I'm just going to write cis for now to simplify the angle. 3 pi over 2 plus 2 pi times 1 for k, all over 3. I'm going to go ahead and think about adding 4 halves plus 3 halves. So that would be 7 halves. And then it's all over 3, so we can think about times 1/3. So we've got 2 times cosine 7 pi over 6 plus I sine 7 pi over 6. And thinking about the unit circle, 7/6 would be right here. And the cosine would be negative root 3 over 2. The sine of 7 pi over 6 is negative 1/2. Then we can distribute the 2 on the outside. So we've got negative root 3 minus the 2's cancel, and it's just 1i. Next, we've got k equals 2, and so we can imagine plugging a 2 in for k. So we've got 2 cis 3 pi over 2 plus, well, 2 times 2 is 4, so we can think about 4 pi all over 3. Again, I'm going to think about turning this into halves. This would be 8 halves plus 3, 11 pi over 2. All over 3 is the same as times 1/3. So we've got 11 pi over 6. And then that would be the same as cosine 11 pi over 6 plus I sine 11 pi over 6. Thinking about where that is in the unit circle, it's right here. And so I know that cosine would be positive root 3 over 2. Sine would be negative 1/2. There's all of this being multiplied by 2. I'm running out of room here, so I'm going to write my final solution over here. The 2's cancel. We've got root 3 minus I. So we've got 1, 2, 3 roots for our answer. That's it for our lesson today. Have a great day.